Okay, let's take a look at chapter 18, confidence intervals for proportions. There's going to be one tricky little calculation, so yes, calculators should be handy, and then a couple of really simple arithmetic calculations to get this done. So here we go. Standard error. We'll get there in a moment. This formula should look familiar to you for the standard deviation. If we're talking about a variable that is categorical, so it's proportions. I mean, it could be binary. Either you're in this category or you're in that category or whatever. Um, if we have a sample proportion, the p hat, provided we know what the population proportion is, p, we can find out the standard deviation that we could use for our sample by taking the square root of p times q. And again, q is the complementary proportion to p. So if p is 0.25, q would be 0.75. Again, they have to have a sum of 1. And then divide by n, our lovely sample size. So that's our formula for standard deviation for a proportion that should look familiar. What if we don't know the population proportion? We're stuck, right? Well, all right. Basically, what we do is, oh, you're going to love this. We take this formula and we change the name. It's now called standard error. But what we're going to do is, if we don't know the population proportion P, we're going to use our sample proportion P hat. And as soon as we know P hat, then we can calculate Q hat divided by n, take the square root. This is now called the standard error. SE is the abbreviation, the lovely acronym that they're going to be using. Okay, so again, it's not the population proportion that we know, it's our sample proportion that we know, p hat. That's what we're going to use here. Yeah, whatever. All right, so for any sampling distribution model with a proportion, it should be centered at the population proportion p. The standard deviation is here. Since again, we don't know the population proportion p, we can't find the true standard deviation, so we need standard error instead. But it should still model a situation where it's centered at p. Okay. Again, I refer to this frequently as the empirical rule. They prefer the numbers to just drill this into your heads. So 68% of all samples will have p hats within one standard error. Okay, so again, we're changing this from standard deviation to standard error here. About 95% should have p hat within two standard errors. 99.7 p hat should be within three standard errors. Okay. Suppose if we want to focus on that 95% level, if we reach out to two standard errors, we're going to have 95% confidence that the population proportion P, remember, we don't know it, we're going to be 95% sure that that population proportion is going to be somewhere in that interval. Okay, so if we go two standard deviations in either direction of P hat, the proportion that we found from our sample, we can be 95% confident that that interval contains that true yet still unknown proportion. That's what we call a confidence interval. Okay? We're 95% confident that the true proportion is going to be somewhere between those two values. Okay? That's a confidence interval. And then the strange graphic. Yeah, whatever. All right, so let's take a moment here, make sure you understand what the basic term means. questions here, what this basic idea is. Pew Research study regarding cell phones asked the question, have you ever received unsolicited text messages on your cellular device? 17% reported that they had. The Pew estimates a 95% confidence interval to be that 0.17 plus or minus 0.04. And if you can't do the math there, 17% plus 4% will put you up to 21. 17% minus 4 will put you down to 13. Okay? So between 13 and 21% of all people have received unsolicited text messages on your cell phone from advertisers. So, for these 5 questions here, are the following statements about people who have cell phones correct? Be very careful in our reading here. Number one, in Pew's sample, somewhere between 13% and 21% of the respondents reported that they had received unsolicited advertising text messages. That is false. Um, they told us it was 17 in their sample. So we don't have to do this, oh, it's between this and this. The statement itself is true, but they gave us the actual sample proportion. They gave us the statistic. Why are they giving us an interval? Number two, we can be 95% confident that 17% of U.S. cell phone owners have received unsolicited advertising text messages. That's false. We are 95% confident that the percentage falls in some interval. We're never going to say we're 95% confident that it is this one exact value. Okay, again, it's a confidence interval, not a confidence number. No, we're going to say 95% confident it's within this range of values in this interval. We're not going to match up a confidence interval with just a single value. Number three, we are 95% confident that between 13% and 21% of all U.S. blah, blah, blah. Yes, 13, the way they've got it phrased there, that's exactly what you're looking for. Number four, we know that between 13% and 21% of all used cell phones. No, we don't know that for certain. We can say that we have 95% confidence that it's true, but we know that it's between them? Yeah, let's not say that. We don't have a 100% confidence interval here. Number five, 95% of all U.S. cell phone owners have received unsolicited advertising. Oh, wow. No, the 95% is our confidence level, not the proportion of people receiving the messages. Okay? Right. Hopefully we're good with that. So, continuing on here, a confidence interval, we're going to use a sample statistic to estimate that population parameter. Again, that's a good deal of what statistics was developed to do. We don't know the actual population parameter, so we're going to estimate it here using our sample statistic. And again, just because we got the results from our survey or however we obtained that statistic, just because we got it, that doesn't necessarily mean we nailed the population parameter, okay? So they just picked some random numbers here and simulated 20 random samples, okay? That nice horizontal green line that you see there, that represents the actual population parameter, the proportion of people saying yes to the question, or again, there's a whole variety of applications here. We take the sample statistic, those are the red dots, And sometimes it's too high, sometimes it's too low. Sometimes you came awfully close. All right, and again, that's sampling variability. That's understandable. And then what they've done there with those blue segments is given a confidence interval. Okay, some of those confidence intervals, most of them do capture that green line. Some of them don't. Okay, so that's why we're not going to say, oh, the population proportion here is somewhere in this range, somewhere in this interval. No, we can say that we have a certain degree of confidence that it's in this interval. 95% of all 95% confidence intervals are going to capture that true parameter. All right. So let's get to actually building our confidence interval. Again, it's going to be high end and a low end. So we're going to take, and again, here's the formula. You can pay attention to this. P hat plus or minus 2 standard errors of P hat. Okay. The extent of the interval on one side or the other is called the margin of error. And again, if we actually do have any elections coming up, you'll hear that phrase over and over again. Um, so again, that's from the center either to one side or the other. The estimate plus or minus the margin of error is, again, you'll hear, well, he's favored 54% here with the margin of error plus or minus 3%. Um, the more confident we want to be, here's one of the strange concepts, strange parts of this. The more confident we want to be, the larger the margin of error needs to be. So we get a wider interval. Okay. We're never going to do something like a 100% confidence interval. Um, for the grade point averages of Fenwick students at the end of this school year, we have a 100% confidence interval that it's going to be between 0 and 6. Well, sure. Yeah, that's a 100% confidence interval because, well, everybody's going to have something lower than a 6. And oh dear God, help us if there's anybody who's got a GPA that's exactly equal to 0. We can say with 100% confidence it's in between, and that's useless. That has no meaning. That's not helpful in the least bit. So, again, if we widen our confidence interval, we're going to have to use more standard errors. Okay? The new and improved 99.7% confidence, sure, we're widening out more standard errors. We have a higher confidence level that we are actually going to capture that population proportion. Now, here's the trade off. To be more confident, we wind up being less precise. We widen this out more values in the confidence interval to be more certain, but again, they refer to it as a balance, sometimes attention. We can be both sufficiently certain and sufficiently precise to make both of them actually useful statements. Um, Most commonly chosen confidence levels are 90, 95, or 99%. But really, you should be prepared to use any percentage. Okay, which brings us through this really strange thing here called a critical value. Um, the variable that you're often going to see here is Z star. Um, they used two standard errors in our 95% confidence interval, but that's more of an estimate, rounding it to the nice nearest whole number, the exact value that we should be using for a 95% confidence interval here is 1.96. That's what we call a critical value. And again, Z star. For any confidence level, we should be able to find the corresponding critical value, the number of standard errors that corresponds here. And now it's time to go to your OneNote. I sent you a tab there that has formulas. All right, and if we zoom in here, hey, look at this confidence interval. We're going to take the statistic plus or minus the critical value, and that's what we're going to look at more closely here in just a moment, multiplied by the standard error of the statistic. Okay, so that's our new little formula you just saw a moment ago. So let's talk about that critical value. In addition to all of these lovely formulas, I'm sorry, some of which we haven't gotten to yet. I'm going to try my best to get there. After that, there's going to be a whole list of tables. Um, so for table A, that's our standard normal probabilities. We haven't used this very much because your calculator will do that for you. And I don't think there's going to be anything on the AP exam this year where you're not allowed to use a calculator. So if you go past table A and you go to table B, again, we'll talk about the difference there between a normal distribution and a t-distribution, critical values. We'll get there eventually. Chi-squared is, I've been told, is not going to be on this year's test. So maybe we'll get to that, maybe we won't. But going back at the very bottom of table B, do you see there how that last line says confidence level C? Read up to the line above it there for 95% confidence. If we're going to go all the way to, from some critical Z score to infinity, the critical value there is what you just saw on that previous slide, 1.96. Okay? So if, say, they wanted a 99% confidence interval, that critical value you would multiply by the standard error would be 2.576. Again, 99% confidence, a wider interval, we're going to multiply that standard error by a bigger value, add and subtract that to the statistic proportion, p hat. That gives us our wider, higher confidence level. Okay, so if they want just a 90%, that's not very common, but there's our critical value. There's Z star of 1.645. Okay, so again, be aware of those, and especially during the test. Oh, 95% confidence interval, I can't remember that stupid number. It's right there at the bottom of table B. Okay, it would be better if you could remember that 1.96. But if you draw a blank that day, it's there. Okay, it's there to help you. Okay, so all right, we just saw, I just mentioned this kind of very, very quickly there. A 90% confidence interval, the critical value is 1.645. Because again, if we're capturing that middle 90% of it, okay, that's leaving off equal amounts to the left and to the right. Okay, hopefully that makes sense. So again, for our 95% confidence interval, we're not really going out all the way out to 2 standard deviations. We're going out to 1.96 standard deviations. So again, we can leave off that extra 5% split evenly left and right. Okay. Now, another thing about your lovely tables here, the other way, and this is far more tedious, if we're looking for a 95% confidence, Okay, as you read through the body here, again, this is if you know the z score, the area to the left of that on our standard normal curve here corresponds to the probability of that popping up. If you know the z-score out to 2 decimal places, that's where table A will allow you to just look this up without using your calculator. But if you look at the values in the body of the chart there, I want you to look for, as I scroll too quickly for you to read it here, not 95% confidence, because again, it's everything from that value all the way down to the left. So if we're looking for the middle 95%, that extra 5%, as I just said, is split evenly left and right. So it's 2.5% to the left and 2.5% to the right. So we're really, if we're looking at table A to find our critical value, we're looking for here an area of 0.975. Okay, and as we zoom in here, I'm looking at 0.9772 is 2.0. That's not right. 0.975. Hey, look, it's right there. And the way you read this, then here's 1.96. Okay, so again, that's where we can find our critical value on this chart. Hey, what are we doing here? All right. So again, if we're 95% confidence interval, okay, they're quoting here of, again, another Pew Research Center poll found that 52% of adults reported hardly ever or never reading a newspaper, and they gave a 95% confidence interval with a margin of error of 1.5%. Okay, yeah, most of that's, you can ignore that just for context. Number 6 in the just checking, if the researchers wanted to be 98% confident, would the confidence interval need to be wider or narrower? If you answered wider, well done. Okay, again, to increase your confidence level, you've got to include more numbers. The range of values there has to spread out, it has to be wider. Number 7, the study's margin of error was about 1.5%. If the researchers wanted to reduce it to only 1%, what would happen to the level of confidence? Would it be higher or lower? Correct answer there is lower. Okay. If the margin of error is less, then the graph is going to be more narrow, or the range of values is going to be more narrow. The confidence level is going to be smaller. Okay. Number 8, if the researchers had polled more people, would the interval's margin of error been larger or smaller? Correct answer there is smaller. Again, if you think back to our lovely little formula, where in that formula do we put n? Okay, if they had put in, they had polled more people, n would be larger, but n goes in the denominator of that lovely square root. So if the denominator is bigger, the margin of error is going to be smaller. All right, again, everything is, all statistical models are based on assumptions. Now again, I find if I can deviate here for just a little bit, all the debate that's going on now about how long we're going to be sequestered. These are all statistical models that are trying to predict how widespread the infection is going to be. And all statistical models are based on assumptions. And now we have different experts on the news just about every single day arguing that, oh, these other people, their assumptions are wrong. My assumptions are right because I'm so smart. Whatever. Different models make different assumptions. If we're basing conclusions here on assumptions that aren't true, then the model's not going to be true. Okay? And we can never be 100% sure that our assumptions are right. Um, we have to check certain conditions. And again, I keep going back to this. I hope you're not sick of hearing me say this. On the exam, you are going to have to write out, you are going to have to comment on every single one of these conditions to verify that the model you're going to use is going to be reasonable. Okay? First of all, the independence assumption. Um, again, from your samples, are they each person in there? Are you are each of these people that you're talking to, are their responses going to be independent of other people's responses? Okay. Uh, were the people chosen at random, or again, if you're doing some kind of an experiment, tossing coins or whatever, um, are they generated randomly? Okay. The 10% condition is the sample size no more than 10% of the population. Again, that goes back to sampling without replacement, like a deck of cards. Okay. The sample size assumption, again, this is from our central limit theorem. We need to check both the success condition and the failure condition. That's why the authors keep referring it to that in this way. Okay. At least 10 successes and at least 10 failures, because otherwise our sample size isn't big enough to use the central limit theorem. Okay, so when we have all those conditions met, we're ready to find a confidence interval. We can go through, and again, using our critical value of Z star, depending upon what confidence level that you're trying to calculate here. So this is basically a summary of our lovely formulas you need to know to build a confidence interval. And again, this is more formulaic. What you'll see on the AP test for your formula sheet is more of a verbal description. I find that curious. Uh, how large of a sample size? That's a huge step in doing any of these surveys, any of these experiments. Um, it's got to be big enough that you're not taking too many people, but yet um, you can't be too small either. Okay, so again, remember, margin of error is going to be that z star times our standard error. Okay, those have to go together. Um, all right, again, don't say, sorry, boom, boom, boom. There's a 95% chance that the true proportion is between 42.7 and 51.3%. It sounds like that parameter value can vary. No, the parameter value is set. We just don't know what it is. We want to suggest a 95% that the true proportion here doesn't move. Okay. Um, keep in mind, the confidence interval makes a statement about the true population proportion. Um, the interval isn't about sample proportions, but the entire population proportion. So don't say that other samples are going to be like yours. Again, we can't be certain about the parameter. That's why we're doing a confidence interval. We're not going to say we're 95% certain that it's this particular value. It's about estimating something about the population, not what you got from your sample statistic. Um, all right, so here's a slightly different one. This is a bad statement. I am 95% confident that between 42.1% and 61.7% of all the sea fans on coral reefs in the world are infected. All right, now that's going a little bit too far there. Again, if your sample statistic came from doing a sample of one coral reef, you can't say that, oh, this is true about absolutely everybody everywhere. The confidence level is about uncertainty. We're 95 or 99 or 90% confident that the population parameter is between these values. Um, we're not 100% confident that we nailed it. Um, now, again, it's trying to estimate that population parameter. It's hopefully somewhere in there. It's going to be closer to one side than the other, maybe. Meh. Um, how precise do you need to be? Well, reduce your confidence level if you want a smaller margin of error. But to get a narrower interval without giving up confidence, you have to have less variability. And hey, take a bigger sample size. Okay. Um, sure, your rounding is part of the work there. Biased sampling, yes. Think about independence, yes. So again, um, critical values are found from the normal model, margin of error. Um, that's based on standard error and the critical value. Here's our new little formula that for standard error that looks amazingly like standard deviation. Um, we can say we've got a certain level of confidence that we've captured the actual population proportion. Yeah, again, the independence assumption, randomization condition, the 10% condition, and again, making sure that your sample size is big enough, the success and failure conditions. Again, those both of those calculations have to be shown. Yeah, I'm gonna always write out the conditions. Don't just say, oh, I checked the conditions and they're fine. Show it. Um, be prepared to interpret the confidence interval as a follow up question to interpreting the interval. Okay? Explain what this means in context. Okay? All right. I hope you got that. Again, like I said, the standard error, you're going to need a calculator to do that. The confidence interval, actually computing those numbers, really isn't all that hard. Good luck with this.